Welcome back to EE 386. This is going to be the lecture for class number 15, and in this lecture we're going to go over root locus sketching techniques, the rules for drawing the sketch, some helpful formulas for your sketch, and some examples. So before we proceed, make sure that you have the root locus handout on Canvas. It's one of Dr. Johnson's original note scans, and it's particularly useful and concise for this topic. Okay. Previously, we had been talking about the standard block configuration, and we've referenced it in a number of our controls design problems for GC design. It looks something like this. Of course, in our examples, we've always had H, the sensor block, B unity. It's just a line, so I've drawn a dotted line in here. Our input is R, or R of S, we're in the Laplace domain, and R is really a reference input. It can be the set point, it can be y sub c, it could also be 0. So it has some variability, and we have the ability to choose this as the input to the system. Y of s is of course our output, and then we had the plant GP and GC that we designed. Okay, we considered again H equal 1 unity line and the control blocks right here. But if we were to extend all of this to a more general case, it would look something like this, where we just had some block here and then some block here, okay? So again, in this diagram, this one really does encompass this one, and R is the reference input, and again, it can be 0, it can be our command signal, or it can be our set point, depending on what our controls task really is, and Y, of course, is still our output. We found the closed loop transfer function before. I believe we've done this example, but you just follow our normal line techniques to develop this by writing the line equation for y, which would be then kg1 operating on this line right here that you would have to label, and then the line here for this line, which you again would have to label, referenced above, and that would be the output is equal to G2 times this Y input, okay? If you combine those lines, you should be able to simplify it, and you'll get this equation right here, GCL, okay? All right, so one thing that we can compare immediately, so I write this out because I want to compare with what the open loop, this is the closed loop transfer function, what the open loop transfer function is. So in general, if you have a block diagram that looks like this, it's very similar to this one I've drawn up here. The open loop transfer function will be the multiplication of these two blocks. Okay, so in that case, that means that our open loop transfer function is this block right here multiplied by this block right here. So our open loop transfer function is kg1, this block right here, times g2, this block right here. Okay, so we've got the open loop transfer function now. Okay, so if we wanted to just kind of simplify this a little bit, we can call g1 times g2 just g. So we make that substitution, and we're left with this equation right here. Okay, so this is the open loop transfer function that we will reference when doing root locus. Okay, now this g right here, and we'll get to that in a moment, it has a polynomial on the numerator and a polynomial on the denominator, and again we'll call that p and q. What we want to do is consider a range of k values. You'll notice that we have k involved in this open loop transfer function. So k can be a range of values, and if we consider this range, some k minimum to k maximum, and usually this is 0 to infinity, or some very large number, then we can go ahead and calculate what happens with the GOL values, okay? So we plug in a k, and we should get possible poles and zeros out for each value of k that we plug in. Now we can see the influence of k in, say, some polynomial right here. I've just written an example. Let's say we have one, we have a GOL, and it has a k involved. And so let's say that the k somehow involves or ends up being involved in one of the polynomials like this, okay? It doesn't have to be QOL, I just wrote one of these right here. And we can see as we vary the value of k and solve for these roots right here, that they go from being an imaginary pair to just a complex pair, so they have a real part now, and then they go to a strictly real pair, real distinct values, and then they stay real distinct values as we increase k. And if you plugged in further k's, you would see that they would continue to increase in magnitude, but they would stay real. So you would normally just plot, and here this is just a plot of roots that I've just tried to show, that you would just mark on the axis where these are heading to, okay? So we start, and now this is the plot that corresponds to this trend. So we would plot first this pair of poles right here, and this is plus minus j, so it's on the complex axis, on the imaginary axis right here, I mean. And then the second pair we would plot out here. So they have a negative real part, so negative 1/2 is this point right here. And then we have a plus minus j value, so they're still in the complex plane. They have a non-zero imaginary part. Okay. As we further increase k, you can see that they become real. So down here, this is the point -5, and so they are on either side of this value of -5. One is far out here. This is about 4.8 or so, so this is somewhere around 9-ish. And then the other one is in the opposite direction, so it's out here. Okay, so it's almost positive. Almost, but it's not quite positive yet. But as we increase these values, they will continue to move out in these directions, like so. Okay, so you can see that although it may be hard to see because I have a dotted line here, I'm trying to show the trend to you, but the movement is going to be down here towards the real axis, and then they move off like that in opposite directions. Okay, so we can say that these kind of form a path. These are migration paths, as we'll refer to them. And these paths are also known as branches. So really, when you have a open loop transfer function, you will have poles. You could possibly have zeros of some kind. They can be two different kinds of zeros, real zeros or virtual zeros. And when you have a certain number of poles, you will have that same number of branches. What's going to happen is the poles will migrate. Okay? Now I don't have, on this plot right here, we are strictly plotting this polynomial right here. We are not plotting the entire function. So this looks a little different from your root locus because we will have poles represented as x's, and then we will have zeros, which are represented as circles. Okay, circles or zeros or o's, whatever you want to call it. Okay. All right. So we're going to see a migration point as we vary that k. So that's really what root locus is. It is the mapping of, or the plotting of, those migration branches. Now, you'll notice that we're using an open loop transfer function. Back here, we are using this function right here, and then our g is going to change for each example problem, for each system that we have. Why are we using the open loop transfer function, which doesn't really encompass everything? We would want to use a closed loop transfer function, right? Well, this is a little more work, and you see that we have k appearing in 2 places here, whereas k only appears in 1 place here. And so, if we can get away with doing a little bit less work, a little bit less calculation, and get the exact same results, why not take advantage of that? And that's really what it comes down to. We're using the open loop transfer function to discover the closed loop stability for the varying k. This happens because the open loop roots and the closed loop roots are actually the same. So if we look at this, GOL, this is our open loop transfer function. And again, we've said that we would have a polynomial on top and a polynomial on the denominator. We can draw out this equivalent diagram using just our open loop transfer function and place it back into our closed loop design. So this is really the open loop portion. This is our GOL open loop block right here. We place it back into that completed diagram for the closed loop system. We'll see that it fits right here in the center. Okay. Now the roots are actually going to be exactly the same. So whenever that happens, that means that since the roots determine the stability, we can determine the stability of our closed loop system just from those open loop roots. Okay. Now notice that when we draw this equivalent diagram, the output y, when we place this back in, it may be different. Now that's caused by a number of different things, but it is not the same for every case. It may well be the same, but it doesn't necessarily have to be. Okay, so we do make a note about that. But back here with the open loop transfer function, so most of our work is going to be examining this guy. We're going to be picking out the zeros. So the zeros are, again, the roots of the polynomial on top, the POL. There will be m of them. We are using m not to discriminate against the m that we were using to differentiate the disturbance. You can still use that. Just please note that those are different, okay? And Q has the order n, that is the system order, okay? And that means that there will be n roots here, or n poles in this case. So roots here are zeros, roots here are poles, and there are m of them, and there are n of them. Okay. All right. So again, we are just varying k over a certain range, and we're graphing what happens with our poles and zeros. Okay. You can think of the zeros as being kind of the end point that the poles want to get to. Like the poles want to move towards the zeros. That's how the migration happens. Okay. And now we'll talk about some rules on how to draw this. Okay. There are rules. Originally there were about 20 that were published by Walter Evans, and his first paper, I believe, is in 1948 called Graphical Analysis of Control Systems. You can look that up if you're curious about it, but we are going to concentrate on the 7 most helpful rules, and they are the first couple of rules. We consider a particularly helpful set of them, and we also are going to consider a few of the formulas that are involved in some of the other rules, and they just help us get a more accurate plot. Okay. All right, so the first one that we'll talk about is called the starting rule. The starting rule states that the branches start from the poles, and that the poles are where k equals 0. So if we were to draw this out, the real axis and the imaginary axis, and say that we had a case where we had a pole at 0, then we would just mark our pole just like so. Say that we had another pole at, let's say, +2, okay? Now, very simply, that is just where we mark our poles. And these are where our branches start. So this is where we would start our locus, okay? This is always the very first thing that you want to do is mark your roots, your poles and zeros, where they are if you have the locations. Now, as far as evaluating the shape of this, the migration paths, the very first rule that you should use is one that we'll talk about. It's actually rule number 3, but the very first thing you want to do is always mark where things are. Okay. So rule number 2 is called the stopping rule, and this goes along with rule number 1. The branches will approach the roots of the 0 polynomial, the numerator polynomial, so that is the open loop zeros. If there are no zeros, then at the approach, they'll approach these virtual zeros, okay? So that means that if we have a same number of poles as we have zeros, everything's fine and the poles should migrate to the 0. There is a 0 for every pole to go to in that case. But as you've noticed many times, there is, say, a case like this. Of course, we've got our K out here, but in this example, I have a pole down here, but I don't have a 0. There is no 0 in this case. Okay, so in that case, this pole would be migrating towards a virtual 0. And we can figure out how many there are. I know that the order of the polynomial in the denominator is 1. So therefore, I should have 1 virtual 0, and we have a formula to figure that out. So you'll take n, order of the denominator, minus m, which is order of the numerator, in this case it's 0. So we solve for that. We have 1 minus 0 equals 1, and we call that number q. Q is the number of virtual zeros. And we have to spell it right. Virtual, just like so. Okay, so in this case, our q is 1. So let's do another example real quick of that. Let's say that we have s plus 2 is now in the numerator. Of course, we've got our k out there. And then we have s cubed plus s minus 1. Okay, so notice here I have no s squared. Does that matter? It shouldn't matter, okay? We can see clearly that our system order for this bottom polynomial is, again, that's the number of poles, but it is 3, okay? So here, n equals 3, and here we see we have a first order on top, so m equals 1. Therefore, q equals n minus m equals 2, okay? So in this case, I would have 2 virtual zeros. Now, what would a virtual 0 look like? Well, something like this. Let's say that I have just a pole somewhere on the real axis, and here's the imaginary axis. I have no zeros, and so what would actually happen is this guy would migrate out along, in this case, along the real axis. We'll get to as to why it's moving on this axis, but he's actually going out here to this virtual 0, okay? And that is at negative infinity, right? Now, if I didn't have a virtual 0, what would it look like, okay? So let me draw that one down here. So we'll have the same case, same kind of side of the plane and everything like that. But now let's say I have a 0 out here and then in the left-hand plane, okay? What happens in this case is that he migrates out here towards this real 0, okay? All right, so I'm using real as in, well, yes, of course it's a real number. It's not in the imaginary area, but it has no imaginary component to it, but it is not virtual. That's what I meant there. Not to confuse you, because we are plotting in the complex plane, of course. But yeah, so you can see the difference between this and this right here, where we would just keep going. So we've already passed this point right here. It just keeps going to negative infinity. Now, if you had a few of these, what would happen? We have our pole here. Let's say we have another pole that's like right out here, and we don't have any non-virtual zeros. In this case, what would happen is we would have some kind of a point where these guys would reach off and go to, and we'll get to as to why they're doing that, towards a virtual 0 up here and a virtual 0 up here. As we add more poles, we'll see that they reach out in different angles around a circle at infinity radius, okay? So that's where all the virtual zeros are. They're all the way out here. You can think of a radius of infinity, a circle, and then we just have the poles going towards different angles of that, okay? And the angle should divide, if you think of like a pie, should divide it evenly. So here we have one up and down, so it divides it in half. If we had 3, it would be in thirds, and so forth, quarters for 4, and such. And again, we'll get as to why as we proceed through these rules. Okay, number 3. This is my personal favorite rule because it is useful in almost every example that we do. The real axis rule states that the locus path will exist on the real axis where the total number of open loopholes and zeros added together, that total number, not their values, but if 1, 2, 3, how many poles and zeros you have, is an odd number. Okay, so here we have the real axis and we have the imaginary axis. Okay, so now we're going to, again, we just fill out everything that we happen to have in this case. And let's put another 0 out here. Okay, so let's say we have a situation like this. How do we fill in the branch? Okay, and this is going to be where you will move your pen or pencil across the paper and you're going to want to look rightward. So you do this and you count the number of elements that you have, and they have to be on the real axis. You can't have a complex axis or imaginary parts counting towards this. Now if you do, it really doesn't matter because you're adding 2 at a time whenever you cross a point, but just notice that all you have to do is count what's on the real axis. Okay, so we move our pencil across here and we look rightward and we count the number of things that we pass that we have on the right. Okay, so I have 0, so that's even, and then I cross this first pole, and then I have 1, so this is odd now. So as long as it's odd, I will fill in on the real axis until something changes. Okay, so moving the pencil across here, we're looking rightward. It's a 1, so it's odd, and it's even. So we stop filling in past this second pole. Continuing moving across here, it becomes odd again once we pass this first 0. So now we get to fill it in until it becomes even when we pass this next 0 and it's even again. So we have 1, 2, 3, 4 past our pencil. Okay, looking rightward. Okay, so we just want to look rightward like that and just move that, and that's pretty much straightforward. So that's how it would go in this case. Now this is not a completed root locus. What's going to happen for something like this, this is incomplete, but it shows application of the rule. Okay, so this is not a completed migration path. Okay, what would happen if we were to go ahead and apply another rule that we'll get to momentarily? This particular plot would look something like this. These two would move towards each other, they'd collide, they'd break out, and they'd break back in to reach these zeros. 2 poles, 2 zeros, each pole should go to a 0 in this case, no virtual elements. Okay? All right, so that is the completed locus. All right, so as I draw these graphs, I am just trying to illustrate the rules. We're not going to complete the locus until the end when we get to examples. Okay, so rule number 4 is the next one. This is the collision rule, and this is particularly helpful with what we were just talking about. Okay, let's say we have 2 branches that are on the same segment of the real axis. So just like these 2 guys right here, these 2 poles. Okay, they move towards each other, and then they collide at some point, some given k value. Okay, so that's why this happens. They jump out just like this. Okay. They deflect off at plus minus 90-degree angles, and that's just saying that there's not any zeros between them. If there are zeros between them, they don't behave this way. Okay, it does rely on them being on the real axis, moving towards each other, and then they will collide at the plus minus 90-degree angles. Okay, so an illustration of this we have these two right here. We use our real axis rule, rule number 3. We fill in this branch right here. Let's say we don't happen to have any non-virtual zeros. What happens is these two move towards each other, and then there's a special k that happens here where they deflect off. Okay, and then they just move at plus minus 90-degree angles here. Okay, and they move towards virtual zeros at this point if we don't have any real zeros for them to reach to. Okay, you don't have to have virtual zeros. You could have a complex pair of zeros, say, or just another zero somewhere else. This could be part of a larger root locus plot, but anyway, they deflect off just like this. Okay, complement to the collision rule. Okay, so this was for the real axis. This is for the complex axis. So in this one, we're going to have a complex pair of poles, just like this. So what happens if there's no zero nearby to interfere with this? They will move towards the real axis. Okay, we can't use rule number 3 for these guys because they aren't on the real axis. The real axis rule only applies to poles when they're on the real axis. Okay, what happens is they deflect off very similarly to the rule number 4 collision rule, but this also can happen with the complex axis. Now, one note to say, this does not always happen. They don't always collide and deflect off like this, but this can happen, okay? So we wrote they possibly collide on the real axis. Okay. And deflect at plus 90 degrees. We'll have to apply more rules to make sure that that is what happens. But when this does happen, they move along the real axis in opposite directions. So again, when they do collide, and that's our migration path right there, then they will move off plus minus 90 degree angles to their original paths, just out here. Okay, again, this is imaginary and real axis. Always want to try and keep your labels on everything, okay? And as we're talking about these rules, again, I'm not labeling the poles as to what the values are, but you would always want to do that. I'm just making up quick examples here. Okay, next rule. Rule number 6, we have the center of gravity rule. Now this only applies if we have the order of the denominator n minus order of the numerator m. So n minus m is 2 or more. So it has to be 2 or more, okay? And then the branches, if this does apply, if this is true, then the branches always move in such a way that the sum of the closed loop roots is a constant value. And then you can find out what that constant value is by just summing all the values of the roots when k equals 0, okay? So that will keep the, you can think about the summation of the root values as being a constant. So, and finally, rule number 7, this is our very last rule that we talk about, the pole zero inequality rule, or equality rule, sorry. If an open loop pole and an open loop zero are equal, they're the same value, then the branch is actually just that root value. So this is the easiest rule to apply. Say we have a pole and a zero being the exact same value, then that's all there is. That is the entire branch, and you are done with the root locus as long as you, let's say, this is a positive 5, for example. As long as you label everything, that is your entire root locus. So it doesn't matter what k is. In this case, we would always have an unstable plant, or unstable system, rather. Because it is always unstable. Okay, so that really completes our rules. Now there are a few formulas I want to go over. Okay, so remember when we were talking about, let's just reference an earlier earlier plot. So remember when we were talking about one of the collision rules right here, and we collide at a certain value on the real axis, we can actually figure out what that value is by the breakaway rule. So break in, break out points are calculated from this rule right here. Now we have a, let's say it was P over Q rather, and so all of this combined, we have the numerator and denominator, okay? So what you want to do is really kind of calculate the maximum of this formula, or I mean this equation. And so you'll take the numerator, whatever this polynomial is, with the k involved, and you will take the derivative of the denominator, and so forth, and have this subtraction here, and you'll just solve this formula, and you will get potential values, okay? So this gives you potential values. All right, so what I want you to be aware of when using this formula is that there will be a solution, as many solutions as the order of this formula, of course, as always with any equation, but that doesn't mean that you necessarily need them all, okay? So say I end up with a fourth order equation here, I solve it, but I only have the case of this right here happening. And I want to find out what this value is right here. If I have 4 solutions, then I'm going to need to look at my plot, look at these solutions, and see what makes sense, and I can choose what is actually the right solution here. Okay, and you may have 2 points where they break out. We had an earlier example where we had this kind of a situation. If we use our real axis rule, we would see that collision rule, they break out, and then one of them, so they'll break out somewhere around here, and one of them at least will reach, actually they'll go like this, break in, one will reach this 0, they'll go over here, reach this 0, and then the other one will also break in, but it will go to a virtual 0. So you might have something like this happen. So in this case, I would have 2 breakout, break-in points as a result. So I would need to look for one that was positive in the real axis, and one that was negative and made sense, okay? So whatever these values are of your pole and your poles and your 0, in that case, you would be able to figure out which one is which, okay? All right, so another formula that we can use is called the angle of the asymptotes, okay? So this would just give you the angle from, we were talking about reaching virtual zeros. We could use the angle of the asymptotes to figure that out, that curvature, okay? And then this is also given in your book. By the way, all of these formulas are in your textbook with the root locus chapter. I believe that's chapter 7, but it does vary for different versions, so you can check that if you're interested in using your book there. But the number of zeros, number of poles, we've already gone over this, and we find that by solving the polynomials. And then finally, we have the angle of arrival and departure, okay? And we can figure out that. So again, we can figure out just total from all of these formulas together where things break out from. We can figure out that point. We can figure out the angle that they lean towards. We can figure out the angle with respect to the real axis, and we can figure out how many branches we have. Okay. All right, so these are all very useful formulas, and whenever we need to, we'll use these in our examples, okay? Some of these are, it's a little more detailed than I would like for you to do in any particular like test problem or homework problem, but I want you to be aware that you can do all of these things. We will definitely use this one, we will definitely use this one, and actually our virtual 0 formula should be on this page as well. We'll just go ahead and write it even though we've had it before. So let's go ahead and see how to proceed for doing an example and drawing a locus. Okay. All right, so let's say for example number 1, we have this kind of a formula right here. You can see that we have a polynomial on both sides, a numerator and denominator. Okay, so how I would approach this is I would first pick out how many zeros that we have. We have m, and that number, if we look at the numerator, is 1, because this is a first order equation, okay? It has at least one s in it. So that is 1, number of zeros, okay? And then I would do the same for the number of poles. N is the number of poles for this example. You can see again, we have 1 down here. It is a first order polynomial. Okay, I now want to figure out how many virtual zeros that I'll have. So I do that by calculating n minus m. And that equals 0. So I have no virtual zeros. Okay, now I want to solve for where are the zeros, or we have 1 0 here. Where is it? And same with the pole, where is that located? Okay, so we'll solve s equals 0, and that means that our 0 is at 0. It's just at the origin. Okay, we now solve the denominator polynomial. S minus 4 equals 0. So that means our pole is at positive 4. Okay, so we can start out our locus by marking those values, and then we'll apply the real axis rule because it looks like these are both real values. Okay, so our 0 is here at 0, and our pole is at 4. So we have 1, 2, 3, and 4. So we'll make our x right there on 4. Okay, label your axis, real and imaginary. Okay. All right, so let's go ahead and apply the real axis rule. Okay, so we'll move our pen across here, and it is 0, even, 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 and then we pass this first pole, and it is odd, because if we look rightward, we have 1 element passed there. Okay, so we can continue filling this in on the real axis until it becomes even, which it does once we pass this 0. Okay, so that's our migration path. Now we always want to indicate the direction poles move towards zeros. Okay, now this is our completed locus. Okay, so as we vary k, what happens in this case is that our pole moves towards the 0, it moves towards the origin. Okay, we can conclude in that case that there really is not a k value for which this system is completely stable. Okay. All right, so let's look here at the next example. We'll do a very similar procedure here. Okay, so what is the number of zeros we have? If we look at this first, this numerator right here, this first polynomial, s minus 2, that means that m, number of zeros, is actually 1. Okay, if we were to just go ahead and see where is that at, we would solve s minus 2 equals 0. We just set it equal to 0, and then we have that the 0, the single 0, is at positive 2. Okay, all right, so let's do the same thing for the denominator. Okay, n number of poles, and you can see that we actually have, if we were to factor this out, we have an s squared term. So this is a second order polynomial, and so we should have 2 solutions to it for setting it equal to 0 and solving. And so we have 2 poles. Okay. All right. The order is the number of roots, always. Okay. So if we were to set this equal to 0, the s plus 3 and s minus 4 polynomial, set that equal to 0, that means that we have poles at -3, that solves the equation to 0, or +4. Okay. All right, so let's go ahead and start our plot. All right, so we have our 0 at +2, so let's mark that guy. That's gonna be 2, and we put our circle there. All right, so we have poles at -3, 1, 2, 3, so that's -3, there goes our x, and we have a +4, so 2 more out here, and we have our x right there. Okay, we can now apply the real axis rule. Okay, if we do that, then we should move our pen across here, and we have even until we pass this guy, and then it's odd up until we pass this 0 right here. So it's even all the way until we pass this final pole. Okay, and then what's going to happen here is that this just continues on to -infinity. Okay, so this can never be even again. If we look rightward, as we move out here to -infinity, we're always going to have 3 on the side of our pen. So this branch just continues on. Okay, so in this case, we have completed our locus, and we will see that we have the root here, the pole here, it migrates towards this 0, and then this pole will migrate towards a virtual 0. Okay, and then that would complete our locus plot. All right, so let's try one that's a little different. In this case, we have just a 1 on top. All right, so again, we want to repeat that same procedure, and we will do a number of, number m, that's going to be the zeros. Okay, so you can see that we have nothing to solve up here. It's just a 1. If there's no s at all, then we're going to have a 0. There's 0 zeros. Okay, number n for poles. Okay, what we would do is we look at the bottom denominator. This is very similar to the one we just did. So the number of poles in this case is 2. Okay, we can calculate q, and we actually didn't calculate q for the last example, did we? Well, we should have done that. So we'll do q n minus m, and that would have given us the 1 that we saw out here. Okay, for example 3, just continuing this, we'll do our q calculation, n minus m equals 2. So we have 2 virtual zeros. Okay, so we should expect to have 2 branches that reach out towards an infinite circle, like a point on that infinite circle. Okay, and they should be completely opposite of each other. Okay, they may be on the real axis, they may be on the complex axis, but we'll see. All right, so let's now solve for what our poles are. So we solve s plus 3, s minus 4, and I believe these are the same as the last example. Okay, so we have a -3 and a +4. So we don't have any zeros, so we have nothing to solve. We can't set 1 equal to 0 and solve anything. That doesn't make sense. So let's just go ahead and mark our, we have no zeros, so we can't mark those, but poles. Okay, all right, so our poles are at -3 and +4. Make one here at -3, and then one here at +4. Okay, so let's apply the real axis rule again. This rule is very handy, told you so. But as you move your pen across here, this is going to be odd. There's 1. And then once we pass the second pole, it's even again. As we move the pen, we look rightward, okay? So what happens in this case, we can apply our collision rule. They're on the real axis, so we're using the collision rule, not the complement to the collision rule. All right, so what happens is they move towards each other, and there's gonna be some point where they break out, okay? Some point, maybe like right here. I'm just guessing right now. We haven't actually solved for this, okay? But whatever K value that is, they break out and they ricochet in plus minus 90-degree directions to their original movement, okay? All right, let's figure out what that point is. That is the breakout point, or breakaway, or break out, break in. Okay, so we can actually solve for this by using our breakout, break-in formula, okay? Remember that was in d derivative, in derivative, d equals 0, where we have numerator and denominator in our original equation. Okay, so if we were to solve for this, we can say that we'll just use the center part here, and our result should be the same as if we did have k involved in it. So in this case should be equal to 1, in derivative is equal to 0. D is equal to s plus 3 times s minus 4, and d derivative, let's go ahead and multiply out d, and we should get s squared minus s minus 12. So d derivative will be the derivative of that, and so we should get 2s minus 1. Okay, so now if we multiply these together in the formula right here, we work that out, we should get that, let's just plug that in. All right, so we have 1 times d derivative times 2s minus 1 minus, let's see, in derivative is 0, so everything else out here is going to be 0. So we're solving for s squared minus 1. And if we solve for that, we get s equals 1/2. It's a positive 1/2, okay? So this value right here is actually positive 1/2. So we can see what happens is these poles move towards the real axis, move along the real axis towards each other, and at 1/2 they collide and they ricochet off at plus minus 90 degrees out towards the infinite circle, okay? So out here and out here. Okay? And actually I don't want to put an arrow on a negative side, but yeah. Okay, so that's our completed locus for example number 3. Let's do example number 4. Okay. In this case, let's see what we've got here. Let's have a GOL of S equals K times, we'll do a S squared. We'll have 2 zeros in this case, and then we'll just do, let's say, keep the same denominator as before. Okay. All right, so the first thing we'd want to do for this case, again, it's the same kind of technique. Number m zeros is equal to 2. So we've got an order of 2 on the numerator. Number n poles here is also 2. So if we're to calculate our virtual zeros, you always can do that, but you can always tell in this case, if they're equal, that you should have a 0 virtual zeros. Okay, so now we find the values of the poles and the value of the zeros, okay? Value of zeros, we've got 2, they're duplicated at 0. So I like to list them out independently if I have a certain number of them. All right, so then we have the value of poles. Okay, these again are going to be the same as our previous example because we have the same denominator. Okay, so they're -3 and +4. All right, so let's go ahead and start our plot. So we've got a 0 here, and we've got another 0 here. It's rare that you have duplicated zeros, but if you do, then just try and show that you have more than one here. I do this, and then if I have a double pole, then I'll do something like a crosshatch like that, and for 3 of them, something like that. Okay. All right, so -3, and then we have a +4. All right, and again, this is the real axis, and we have our imaginary axis. All right, so let's apply the real axis rule. Surprise, surprise. It's very handy when you have anything on the real axis. So we move our pen across here, and we just fill in this branch because it's odd past this first value, but then we add 2 poles, and it's still odd. Okay, and then if we look past here, we have 1, 2, 3, 4, so it's never again going to be odd looking rightward. Okay, oh, I did not label values. I need to do that. There we go. All right, so this looks pretty simple. You can see that we are going to have poles moving towards the zeros. They just move towards the origin. Okay. All right, so the poles move towards the origin, where the zeros are. Okay, now let's look at our next example. Oops, I seem to have written another example 4. Okay, so we'll make this, instead of example 4, it's very similar to example 3, so we'll make this 3.5. It really doesn't matter what value it is, it's just a different example. Okay, but it is very simple because we kept the same denominator, so we'll use that excuse here to call it 3.5. All right, example 4. Okay, so we've got an s over an s plus 2. Okay, all right, so same technique, number m and number n. Okay, we have 1 0, we have 1 pole. Okay, and then in this case, we can solve for the 0. You can see that that's at the origin. And we can see that we have the pole at -2. Okay. All right, we could just fill this in, and this is actually a very simple example. I'm surprised I wrote that out. I may have meant to have it squared or something, but at -2, we're going to do lots more examples, so no loss here. We just fill in that branch as we have been. And that is the entire locus right there. Okay, so we migrate towards the origin, just like that. Okay, if we did calculate virtual zeros, we would see that there's a 0. If we did calculate the breakout, break-in, obviously you can see that that does not happen in this case, but let's go ahead and see what would happen if I didn't know that. And I just wanted to go ahead and calculate and see what happens. Well, we write out our formula. And so we know that n equals s, and then d equals s plus 2. And so n derivative is equal to 1, and d derivative is equal to 1 as well. So if we plug into our formula, we have s times 1 minus, and that's n derivative, that's 1. So if we were to solve this, let's just double check, we have an s times a 1 minus a 1 times a, whoops, we left out that d, times a s plus 2. Okay. All right, so it looks like we've got s minus s, which is 0s, and then we have just a -2, okay? And that doesn't really make sense at all with respect to setting this equal to 0, so we can't have that at all. So we have something that does not make sense, it doesn't solve correctly. So in that case, we can see that we definitely do not have any breakaway points. We don't have any possibility of them. Okay, so we'll just write that conclusion. Right? If this doesn't solve, and of course, you know, you don't have any breakout points, but let's say I solved it and I got a value of positive 15. So that would be like something over here. I would also be able to disregard that. It would not be a solution that made sense for within any of my branches. My branch is just between the -2 and the 0. And so if it's out here at 15, then there's no way I can break out at 15. Okay. All right. Example 5, we have this situation right here. So number m equals 1 because we have just an s on the top, so it's a first order equation. Number n equals 2 because if we were to FOIL this out, we would see we have an s squared term as our highest order. It's a second order polynomial. Okay, so we can solve for where the zeros and poles are at. 0 is, of course, still at the origin. It's the same as example 4. And if we solve for the poles, so we see we have a double pole at positive 4. Okay, let's calculate Q. Again, if we did that here, Q would equal 0, but here we can see that Q in minus m is actually 1, so we will have one virtual 0. We should expect to see that. And as we fill in our root locus plot, or rather the word locus, that is, that's the same as saying plot. It's a certain type of plot, so it's a root locus, not a root locus plot, but I often say that plot anyway, so oh well. Anyway, so we'll plot 0 at 0, the 0 at 0, and then we have the poles at positive 4, so 1, 2, 3, 4 out here, and we have a double pole, so we have 2 of them. All right, so let's use, since we have items that are on the real axis, let's go ahead and use that real axis rule again. And so if we move our pen across here, we have even, because it's 0, 0 is to even. And then it's still even, because we have 2 if we're looking past here. But once we pass this 0, it's odd, because we have 3. So we can fill this out, and it actually goes all the way out to negative infinity. Okay? And so that that kind of symbol, the just the jagged zigzag, is kind of like there's a lot of space, but nothing interesting happens. So I tend to use that in cases like this. Okay, it does kind of look like a resistor though. If you're EE or you've taken one of the circuits courses or something like that, you'll recognize that resistor kind of symbol. But anyway, so what happens here? Well, we know that the poles have got to get over to this 0. One of them's got to go to an imaginary 0. Sorry, I use the word imaginary. I mean virtual 0 out here. And one of them has got to go to this actual non-virtual 0. So it looks like they are going to have to break out. Now, we can't just draw a path over here because that's not our migration path. We're going through very careful rules to fill out these migration paths. We can't create one, but what should happen is that these are going to break out here, so we should use our breakout formula and break back in over here. One goes this way, and one goes that way. This is very similar to an example when we were talking about the rules that I drew out. But let's see it happen. Okay, so let's use our breakout formula. All right, so there it is. That's our formula. Our n is equal to s, that means n derivative is equal to 1, okay? And then if we were to write the d is, let's say, s squared, and I'm just going to FOIL this out, and minus 8s, okay? And that means that d derivative is 2s minus 8. All right, so now we plug this into the formula. We've got s times 2s minus 8 minus n derivative, which is 1 times the d, which is 2s squared minus 8s plus 16. And we set all of that equal to 0, just as in the formula. Okay, let's multiply this out and simplify it where we can. So we've got 2s squared minus 8s minus s squared plus 8s, and then minus 16. We have to distribute that negative sign. So this was a minus, that was a plus, and then this was a minus, and all of this is equal to 0. We can still simplify this a little bit. So we've got, combining these two terms, s squared, and then these two terms, it looks like, cancel out, and so they don't go into this bottom formula. And then we've got the negative 16. Okay. All right, if we were to solve this, then we would get that if we plug in 4, so s squared equals 16 in that case, we would see if we plug in 4, of course that works. If we plug in negative 4, that also works. So plus or minus 4. So we have two solutions. All right, let's see what makes sense here. Am I going to have a breakout point? Yes, I am. I'm going to have to. So that these guys can come over here and reach in, but there's also going to be a break-in point, right? So I have two solutions. In this case, both of them are useful because I have this point 4 where both of my poles are. There's no direction over here or over here that they can go to before they break out. So it has to be at positive 4. So yes, indeed, that is my breakout point. So we break out at positive 4, but we're going to break in, since this is the left hand plane here, all this is negative, we're going to break in at negative 4. Okay, so over here at negative 4, that's where we're going. So just move over here. Now it is possible to tell, normally, you know, if you have, say, two, in this case, we have a double pole at a single value, so it really doesn't matter, they're the same value. But it is possible if you have two different poles, and they come over here, they move towards each other, they deflect off, and then they go over here. Say our poles were at like positive 3 and positive 5, so they would have to move towards each other and then break out. We could tell which pole went towards the 0, or which one went towards the virtual 0. Okay, but in this case, we can't tell that because they are the same value. There are formulas to do all of that. I'm not so much concerned about you knowing that level of preciseness as much as the shape and drawing conclusions from the plot. Okay, so this is the correct shape. We do have the breakout, break-in points marked, and so this would be sufficient for an answer in this case. We have marked all the poles, all the zeros. We have the direction labeled. We have all of our migration paths. So how many branches do we have? We have the branch going up here and over here. We have the branch going up here and out here, okay? And so we are able to tell what happens with this plot. And that's much more important to me than knowing just the level of which goes where in terms of in what we're talking about. So yeah, so this would complete this example. Okay. All right. Let's do a few more examples. Let's see. So the difference between example 5 and example 6 that I wrote out is that we no longer have this s, okay, on the numerator. So otherwise, it is the same example. We've just lost our pole that we had. So we have no, I'm sorry, we lost our 0, no zeros, okay? And that means that m is equal to 0, okay? We can see that n is equal to 2. We can use our results that we went through in the last example. And then that means that we have +4 for the pole values. Okay. Go ahead and plot this. And in that case, 1, 2, 3, 4, we have again our double pole. We have no zeros, and so we use our right-hand rule, or I'm sorry, not right-hand rule, real axis rule. We'll move our pen across here. It doesn't do anything for us because it's even the entire time. Okay, we're a 0 out here, and then we're 2 once we pass these 2 poles. So it's still even, so there's nothing to fill in. Okay. In this case, what we would need to use is our collision rule. So they're actually on the same value, but the result would be the same as if we had a +3, or actually even a -3, and a +5. And they move out here towards each other, and then they would collide off. But these two just happen to already be at the value that they'll collide off of. So what's going to happen is they will move towards ±90-degree values from the real axis, okay? All right, and so that would actually complete your locus. In this case, of course, we would have to label the 4 right here, but we can use the breakout, break-in formula again. So if we did that, we would just write out a formula first, n. Okay, n in this case is equal to 1, n derivative is equal to 0, and then we have, from our previous example, we have the same d value. Just multiply that out. Okay, if we plug this into the formula, then we would get 2s minus 8 minus s squared, or actually that's multiplied by 0, and derivative is 0. So we could solve that, and we would get s equals +4. Okay, so that is our single, there's only one solution, single value for breaking out. Okay, does this make sense for our plot? Yes, it does, because our poles are actually at 4, and this is where they should go. Okay. All right, so that's example 6. Example 7, this is a similar example, except in this case we have an s squared. Okay. All right, so again we have no zeros. Okay. M is equal to 0. All right. But we can say that we do have 2 poles, and we have a s squared term, so n equals 2. Okay, again, I keep forgetting to write out the q, but q should be 2 up here, and q, let's go ahead and calculate that, n minus m, so 2 minus 0, we should have 2 virtual zeros, again. All right. So what are the values of our poles? S squared, we have to solve s squared plus 4 equal to 0. Okay, if we solve that, we get s squared equals -4. Okay, all right, so that would be s, solving for our root there, equals the square root of -4, which would then be plus minus 2j, or j2, however you write it. Okay, so we've got a complex pair for our poles. Well, that's good because we've done a lot of simply real axis-based examples so far, so it's about time we had a complex one. Real axis right here. Okay, so let's go ahead and plot. We have no zeros, So we can't put any zeros down here, but we have two poles and they are plus minus j2. So we'll have one here, we'll have one here. Okay, so this is at plus 2 and minus 2. And then that's the origin right there. Okay, so does it make sense to apply the real axis rule? No, it does not. There is nothing of interest on the real axis as far as our system goes. What else can we do? Well, we know we have two virtual zeros because we calculated that out. We do have, instead of the collision rule, we have the complement to the collision rule. So we have these two poles right here, and we know that in the complement to the collision rule, if k increases such that they move towards the real axis, well then they're going to probably collide and deflect off at plus 90 degrees. Just like that. And then we have moving out here to negative infinity, and then out here to positive infinity, just like so. Okay? Now, does that make sense? Well, what we can do is use our breakout break-in formula just to verify that yes, this does happen. If it does, we should have a value right here, which will probably be at the origin. Okay, so let's find that. We'll rewrite our formula. Oh, whoops. No, tick mark right there. Okay, here we go. And so we just plug in our values. So n is again equal to 1, and n derivative is equal to 0. D is equal to s squared plus 4, and that means d derivative is equal to 2s. And so let's plug that into the formula. And so we have 1 times 2s minus 0. So that, that whole second term, we don't need to do that multiplication. All right, so that means that 2s is equal to 0, or in other words, s is equal to 0. So this is a root, this solves. We get a value, so it should happen at 0, so we break in. So indeed, these actually do collide, and they do deflect off. So that's how our completed root locus would look like. Okay, so we have these two branches going out to plus minus infinity in that case, and they are 90 degrees from their original paths. Okay. All right, so now let's do a bigger example where we have a few more poles. So we have 4 poles in this case. So n equals 4 because we have a fourth order equation, and m is equal to 1 because we have just a first order equation up here on the top. Okay, so our 0, we can see from the s plus 3 on the numerator is at negative 3, and our poles are at, if we go through here and look, and if we set this equal to 0, we would have s equals 0, negative 1, negative 2, and negative 4. Okay. Let's go ahead and find q. So q equals n minus m equals 3. Okay, so we should have 3 virtual zeros. Okay, so we'll start our plot, we'll mark our values, and then we'll assess from there. All right, so we have a 0 at negative 3. Let's take care of that first. 1, 2, 3, that's negative 3. Put our circle there. We have poles at 0, so an x here at 0, negative 1, so an x right here, negative 2 right here, and then also at negative 4. So everything out here up through negative 4 is encompassed with a value of a root from one of our sides of our equation. So let's use the real axis rule first because we have a lot going on the real axis. So we move our pen across here, and it's odd once it crosses this first pole. It's even once it crosses the second pole, and then it turns odd again, the sum of elements on here, once we cross this one up until the 0. Okay, All right, so if we look past here, we have 4, so it's even until we cross this pole at the -4. So we have 5 elements right here. Okay, and then we can do our negative infinity little resistor mark. Okay, there we go. All right, so does this make sense? Can we say that this is done? Nope, because every pole is not going to a 0 or a virtual 0. So I know I'm not done yet, but I'm on my way. I have these two right here where I have a pole going to a 0. So I can go ahead and mark the direction on this one. Okay, how do I know that some other pole is not breaking in here and then causing this one to break out? That doesn't really make sense because we have a single migration path right here. Now that would be revealed in using the breakout break-in formula. We would have no value in here if we solve that. Okay, let's actually go ahead and use that because we can see that we have to have something happening here in order to reach a virtual 0. Okay. All right, so let's write out our formula. N d derivative minus n derivative times d equals 0. Okay. In this case, n is equal to s plus 3, and d is equal to the whole denominator here, s plus 1, s plus 2, s plus 4. Okay, n derivative is equal to 1, and d derivative, in order to find that, you would have to multiply all of this out. So let's go ahead and do that, and we should end up with s4 plus 7 s cubed plus 14 s squared plus 8s, if you multiply that out. And then the derivative then of d should be 4s cubed plus 21s squared plus 28s plus 8. All right, so let's plug that into the formula. So I'm going to write out n d derivative minus s, or I'm sorry, n derivative, goodness. It's very easy to make a mistake, but it's much better when you catch it immediately. So we just plug in our s plus 3 from our n, and then the d derivative, which was this value right here, minus n derivative, which is 1, times the d value right here. So s4 plus 7s cubed plus 14s squared plus 8. Okay. All right, so we would solve for that right there. Now, whatever values we happen to find from this, we should get the values of the break-in, break-out formula. So I went ahead and I did that multiplication. So it turns out that our values, though, I haven't solved for that yet. So what we would need to do, let's go ahead and combine this, and we can find our final resulting equation. Okay, so what we've got here, 4s fourth plus 21 times s cubed plus 28s squared plus 8s, and then we have the plus 3 multiply, plus 12s cubed plus 63s squared plus, and that's 3 times 28s plus 24, and then subtract it off from s to the 4th plus, or rather minus 7s cubed minus 14s squared minus 8 equals 0. Okay, so we could go ahead and combine this, and we should find out. I don't feel like doing this on video. I feel like it will take too long, so I will post the answer to this in the Canvas announcement, okay? But we should find that we have a breakout point that happens right here. We'll call that alpha. So in this equation, we will have 4 values for the solution. Okay, let's call those alpha and beta and gamma, and we'll have the triangle delta. Okay, we should have an alpha and a beta that makes sense for our equation. So we break out at alpha, and we break in at beta. Okay, and again, one of our poles is going to go this way, and one is going to go towards this. Actually, no, that's actually a that is a pole. Sorry, for a second I was looking at this 0. So this shape is actually wrong, and that's how you know that these videos are filmed fresh, because I do make mistakes sometimes when I draw this. Unfortunately, I'm using a pen too, so I can't erase it. But anyway, we should come out with a deflection that looks like this, just with our collision rule, our regular real axis collision rule in that case. This pole is going towards this virtual 0, and since we have 3 virtual zeros, this totally makes sense that this pole is going to this virtual 0, this pole is going to the actual 0, and then these two move in and break out and go to virtual zeros out here. Okay, now if we used our angle of asymptotes formula, what we would see is that the shape, sure, this one remains the same and this one remains the same, but these two out here will sort of have this look eventually. Okay, so you can think about it. Remember what I was saying is it divides the circle evenly. We'll have this line, and then we should have kind of like that line, and it divides the circle into thirds. If you think about it, the number of virtual zeros, that is, the paths to reach those virtual zeros is what I'm talking about. That's what divides the circle. Okay, so they'll have this kind of look. All right, so sorry about that, and I hope that doesn't cause any confusion. Always make sure you're looking at the right pole, not a 0 that's already spoken for with this pole. So yeah, so that'll be example 8. Let's do one more example. I have this one written out as well, so we'll go ahead and use this one. All right, so M, for this one, we have a first order equation. We have one of those, just one, M equals 1, and then N, we have a third order polynomial. N equals 3 in this case. Okay. All right, so we want to find, again, the values. So the 0 is at -1, and the poles we can solve for by solving s cubed plus 4s squared plus 6s plus 4 and set that equal to 0. And I believe I went ahead and did that. Get that value for you. Yes, okay, good. So the poles will be at -2 and plus minus j, positive 1 plus minus j. Okay, and we can solve for q. We'll want to go ahead and do that. We have an n minus m, and we should have 2 virtual zeros. All right, so let's go ahead and plot what we've got so far. All right, real axis and imaginary axis. All right, so we've got a 0 at -1. Let's go ahead and plot that guy out here, -1, and there's our circle. All right, so our poles are at -2, -2, there's our x, and then +1 plus or minus j. So 1 here and 1 here. So good, we've got more complex cases. All right, so I do have 2 elements, two roots of some kind on the real axis. So that means that I can use the real axis rule in that case. It's only useful if there's something on the real axis already. And it doesn't matter that you have complex poles or zeros. You can use it as long as you do have something on the real axis. So let's go ahead and use that. When we move our pencil across here, and it doesn't matter that we cross these guys because they're a pair anyway. Move this across, and we have 1, and so that's odd until we cross the -2. Okay, now it's even again, looking rightward, so there's nothing else. Okay, so we've got this path right here. Well, this makes sense, and so this pole would move towards this 0, so we have our direction down. Okay, we now have these two poles right here. What happens when we have we don't have any? We have 2 virtual zeros, we know, but we don't have any zeros for them to move to. Well, we had an earlier example where these moved to the axis and then they deflected off. Well, that really can't happen because we've already filled in all the migratory paths out here. Okay, so using the complement to the collision rule won't do us any good because we know that cannot happen in this case. All right, well, what's actually going to happen, and we can solve with our breakout break-in formula as well. And actually, good, I went ahead and did that. 1.6, I will put that other value on Canvas though. Breakout break-in formulas. If you solve that, you should get 1.6 plus or minus j 0.65, and then a value of 0.34. Okay, let's see, does that make any sense for our plot? Okay, so the plus minus 1.6 is the negative 1.6 is actually right here in this path. Okay, well, that does make sense, but then it's got imaginary value, or a complex, yeah. It's got an imaginary part to it. So we really can't break in, break out of that. Okay, so these two values don't make sense. All right, and then we've got a negative 0.34, which we know is in this area where we don't have any path. We already used the real axis rule to fill in our real axis parts of our path. It's not in that dark part. So this value doesn't make any sense. So we know we actually do not break into the real axis at all. What's left? Well, they just deflect off at virtual zeros. Okay, at opposite directions. Okay, just like that. Okay. Again, if you use the angle of asymptotes formula, what's going to happen is you're going to move these are going to tend towards dividing the circle into a third. Okay, so we've got this slice right here, and then we've got a slice going this way and a slice going this way into kind of that look right there where each portion is 1/3 of that infinite circle. Okay, all right, we'll just do this conclusion for this final example, and we did it for at least one other example. Is there a k value where this is going to be stable? And the answer is no. These are always in the right-hand plane, these poles. There is no k value that makes them all shift back over here. Okay, so this is unstable for all k. All right, so hopefully these examples help you a bit. Let me know if you have any questions, and I will see you next time when we start to go over Bode plots. All right, see you then.